Hello class, this is Mr. Lehman. Today we want to talk about Unit 5, ionization energy. It's another trend, the third trend that we're looking at on the periodic table. And so we already looked at atomic size and ionic size. And so we're going to look at ionization energy, which is how much energy is required to steal or to remove the outermost electron from an atom, or the valence electron from an atom. And what we're going to see here is that it sort of falls upon the same principles, relies upon the same principles that we talked about before. Distance away, how far is an electron away from the nucleus, how far is it away from that force of attraction trying to pull it in, and also what charge from the nucleus is able to reach and pull those outer electrons in. So let's go ahead and talk. So quick review, effective nuclear charge. You have to understand this to understand the trend of ionization as we go left to right. And so remember, effective nuclear charge, the ENC, is the amount of the positive charge from the nucleus that is able to reach and pull and try to attract those valence electrons. So not all the positive charge from the nucleus. So if there's 11 protons in sodium, not all of that positive charge is able to pull on the outermost electron, because remember the concept of shielding. All the inner electrons, all the core electrons will shield some of the positive charge from reaching the outermost electrons. And so we can think of inner electrons as being like blockers, shielders, and we can think of the valence electrons as like the running backs. So the running back hides behind the blockers. And so let's take a look at sodium. Alright, so I already had this one drawn for us. So sodium has 11 protons, 11 electrons. And so for ionization energy, we're trying to figure out how much energy is required to steal that electron right there. So we have to figure out how much charge from the nucleus, how much of this 11 positive charge is pulling in that electron. And so the way we do that is we take the number of protons, which is 11, we subtract the number of inner electrons, 2 in the first, 8 in the second, so 2 plus 8 is 10. The difference is how much of the positive charge from the nucleus pulls in that electron, or the effective nuclear charge. And so this electron is being pulled in with a very weak 1 positive charge, whereas sulfur has 16 protons, 16 electrons. And so as we go across the third period, we go to the sulfur, trying to figure out how much of that positive charge, how much of the 16 positive charge are pulling in these electrons on the outside. And so we take number of protons, 16, minus number of inner electrons, which is still 2 and 8, 10. So 16 minus 10 is 6. So that tells us the effective nuclear charge. These electrons on the outside are being pulled in with a 6 plus charge. And that's why, atomic size-wise, sulfur is a smaller atom than sodium, because sulfur does a better job of pulling in these outer electrons and pulls them in tighter, whereas sodium's one electron is able to stay a little bit farther away, making it bigger because the force pulling it into the nucleus is less. Alright, so same thing. So if we're trying to steal an electron from sulfur versus sodium, and they're both 3 shells away on the third shell, disregarding size because it plays a secondary role here, we're just looking at the positive charges pulling it in. Which is easier to steal? Is it easier to steal this electron is being pulled in by a positive 1 charge, or this electron here is being pulled in by a 6 plus charge? I'm simplifying things here, but 6 plus is 6 times greater force than 1 plus if we disregard the distance. And it would be much, much harder to steal, it would take more energy to steal from sulfur. And so if we look at our periodic table, the trend for ionization energy, the energy required to steal an electron, will increase as we go left to right. And once again, we're not worried about the transition metals 3 through 12. Just looking at the main group elements, group 1 and 2, and 13 through 18. So as we go left to right, it's going to get harder to steal the electron on the outside because the force, the positive force in the nucleus, the effective nuclear charge is pulling in those outer electrons increases. As we go down a family, remember we said atoms get bigger, so everything in group 1 has an effective nuclear charge of 1 plus, and so if we stick with the same family, the only thing that's changing is that that electron is getting farther and farther away from the nucleus, and the farther away 2 magnets are from each other, the easier it is to separate them, the easier it is to remove the magnets from each other, because the farther away 2 magnets are, the weaker the attraction. Alright, so as we go down a family, atoms get bigger, the valence electron gets farther from the nucleus, and so the amount of energy required to steal the valence electron decreases. It gets easier. One other thing I want to look at is something called secondary, or not secondary, the second ionization energy, third ionization energy, successive ionization energies. So if we look at sodium, once this one electron is stolen, I forget the exact number, it's like 500 kilojoules per mole of energy required, give or take a few kilojoules. Once this outermost electron has been taken, we're now down to 10 electrons. And there is no more third shell, right? So sodium has a full octet. It's very, very happy. The second shell is full. It has 8 electrons in the second, so it has a full octet. It's very, very stable. Why is it very stable? Why is it hard to steal another electron from sodium? Why is it hard to steal a second electron? It takes 9 times approximate more energy to steal a second electron than a first electron, because let's look at the effective nuclear charge. We still have 11 protons in the nucleus. There's still 2 electrons in the first, but the 8 electrons that were shielding the outside before are now the outer layer. So these 8 electrons in the second are no longer shielders or blockers, but they are the valence shell. And so of that 11 positive charge, there's only 2 electrons that are shielding the outer shell. So 11 minus 2 is 9. So these valence electrons are being pulled in with a very strong 9 positive effective nuclear charge. So not only is the electron one shell closer to the positive charge, but it's being pulled in with a 9 plus charge instead of a 1 plus charge, and that's why it's approximately 9 times harder to steal the second electron from sodium, which is really impossible for atoms, another atom in nature, to come along and steal it under normal conditions. So sodium, once it loses 1 electron, it loses 1 electron very easily, but it never loses a second electron very easily, almost never, because it takes way too much energy. Alright, so it's really hard to steal an electron that was on the inside. Alright, that's it. I hope it helps. Have a great day.